I'm Sean Henry. I'm a product manager at New Relic, and this is my colleague.
Hey, I'm Brian Galeno. I think this thing is on. And I guess what we're going to talk about today is some future stuff. By the way, before we go into what we're talking about, I'll just say we're both product managers, so we may talk about some things that are on the verge of coming out. So, take it as you wish. But we're going to talk about going beyond the basics. I know some sessions earlier were about some basic labs. We're going to go deeper, beyond the basics, and talk about how to increase the reliability of primarily your NRQL alerts, and also reduce the time to detect. Sean, any colorful notes to add?
No, I just want to stress that this is mainly focused on NRQL alerts. So if you're thinking about APM, browser, mobile alert conditions, we won't really be discussing those a lot today because all of the new and great stuff we have is all coming out for NRQL alerts.
And not to say that you cannot use NRQL alerts to monitor all those types of data. However, the NRQL alerting is the area where you work in to go deeper.
Indeed.
Right, you're right page here. So at a high agenda is this. We're going to talk about some high level things. I'm going to give you a little brief demo, and I'll call it a slight sneak peek because things are rolling out next week about a new incident response experience. So we're going to show you that. Then we're going to talk about how the alert system works at a high level so you have the right framing and understand how to think about this model, right? We're going to talk about sort of how the pipeline works. It'll get a little complicated seeming. We're going to talk about how to make it easier. And we're going to go back into the complicated stuff again, going deep again. Then we're going to wrap it up by talking about how to apply that complexity to different use cases and best practices. Right. So let's first do a brief demo of the incident response process, right? And see if I can navigate my tabs here properly. That's not a sign of confidence here. I'll have to stop that sharing first. That was why. Okay. Let me stop the full screen. Here we go. So in this view here, this is, again, a brief sneak peek. This may not be what you expected to see when I said, let's take a look at the incident response pages. So oftentimes your incident response lifecycle begins by receiving a page, an email, some sort of notification that says, hey, there's an issue, there's a problem, right? And follow this link, read about the information in the notification, but follow the link to find out more details. So this is the part that we're rolling out a new, richer experience for. And this is available to everybody. It's not unique or distinct. It's available to everybody on the New Relic platform. And so in this new world, we'll be referring to the high-level aggregate roll-up thing as an issue, right? We detect small things. We identify these little violations and say an incident has happened. We roll those incidents up into an issue. We bring a bunch of other information together, meta information relationships together. We do some analysis on that thing, and we call that thing the issue. That represents the problem that is happening at a high level and the thing that you're going to work on to discover a root cause, right? So typically you will come in from a notification land at a particular issue page, but when you come back to work on that issue again, you'll see this high-level area here over in issues and activity, right? So here in this issues list, this will list all the issues, either closed or active or open issues that you're looking for. In this situation, I am the owner of the fulfillment service, and I am having a problem. So I'll type in fulfillment. If I typed it correctly there, yes, I did. And I'll find the 4 issues that were open at this point in time that deal with the fulfillment service. Now, how do I know these deal with the fulfillment service? In this particular case, they don't all tell me that they're part of the fulfillment entities, but they came up because this search found deeper incidents that dealt with that particular service. So let's take a look at this one here. CPU percentage greater than 45, at least 5 minutes. I happen to have that here in this tab here. So what we're doing here is taking a look at the issue. Like again, the issue is meant to give you a forest level view, all right, a high level view. And we have the title that was generated mostly from the first incident that it popped up. But we can see that this issue contains 8 incidents. 8 incidents happened that came together to create this issue. And we correlated those issues together, the incidents together in one issue, right? You can scroll and see them all here in the list. Okay. But before I dig into each one of those individual issues, and I can see some entities that are related to it, let me scroll down and say, okay, let's first try to see if we can point you towards some possible root causes. Here, if we have any deployments happening or integrated with this particular set of entities, they would show up here. Now, I can give you a little peek here at another environment that actually does have deployment set up. And you can see here for this issue, it said, well, at about the same time these incidents happened, there was this deployment event that happened from Greg Parker, and maybe we should dig into that. This is a possible cause due to the proximity to this issue being created, right? Let me hop back here. Now we can see error logs. These are the error logs, the logs from the context of these particular entities in this time frame. So you can see, oh, I do have some error activity, and I could dig into the error logs there. I'm not going to do it now because we're actually going to get back to a different topic area. And here, if there were some attributes to investigate, we would dig into those as well. But what I really like here too is an overview of the entities that are involved in this issue. This gives you a map-based view. You can click on the list-based view as well to see the 4 entities involved here. There they are. You can show more. But again, I like this map view. This map view is pretty swift here. And one of the cool things is here's that fulfillment service that I own. Great. I can see some golden signal activity of what's happening here at a high level. I can see its context, where it's running on different hosts. Right. I can show the entity preview. I can get context to what's happening right there along the side. I can see a history of activity. I can see some tags for context. I can see some other golden signals happening here, right? And even more context. Very nice, very nice. And then I can see the flow. Let me get rid of this little pop out here. I can see that some of these incidents cascaded in over time. I can see they sort of resolved at a bit of a ragged edge on the end. This helps me understand what's happening at a high level, or I can pick one of these individual incidents and dig into it in more detail. Again, click on the incident, it slides out, and now I can see the specific incident. Historically, we've referred to this as the violation, right? The one signal that has been violating a threshold over a period of time, and we see that chart here, right? And on the right-hand side, we see more context. Again, more tags to help us understand what that item is, the high-level time frame of when it started to degrade, when it recovered, right? And here we're going to try to span out a little bit, bring the power of New Relic to this moment. Look for other attributes, look for any anomalies that we may have found, or here in this case, look for errors that are happening at about the same time, right? So this is just to show you the power that is available to you in the incident response flow when you have taken the effort and sort of invested the time to configure incident detection appropriately or ideally, right? Now, let's jump in a little deeper. So here on the right-hand side, we see the conditions, the policy that this thing belongs to. So in our situation, we're talking about looking deeper at NRQL conditions. So, this is what an NRQL condition looks like as a whole. I'll just point out a few broad areas. Obviously, you have the name, you have some metadata at the top, you have the area that defines the signal, you have the area that defines your thresholds, the sort of criteria you're looking at to be to identify when that signal is violating, right? And here you can get deeper and go with some advanced settings. And that's what we're talking about today, these advanced settings. Let me bring back to this slide here. And with that, I'm going to let Sean take us back into talking about going deeper. John, do you want to take over the screen share from there?
Yeah.
I will start screen share.
Working on that right now.
That button here.
Hey, there we go. All right, so I'd like to take a look at the high level to let you know really how this new streaming alert platform works that we have. And keep in mind that we're talking about NERCL alert conditions here because they're usable for every purpose. So from an in-orbit view, this is a very high-level view. What does the streaming alert platform mean? Well, basically, we've got a source of data that could be your agent. It could be a cloud integration service. It could be a third party like Prometheus or Nagios. It doesn't matter. But the data is coming in from that, and it's coming in through our ingest pipeline. Once after it hits the ingest pipeline, of course, it gets shunted off and gets put into storage in New Relic's database, which we know as NRDB. Once it hits NRDB, you can query it using ad hoc NERCL queries. It's going to show up in dashboards and so forth. But our alerts system sits off to the side here and monitors the data as it's streaming in. Before it even comes to rest, the alerts platform is watching that data because we want to reduce mean time to detect. And the way you do that is not by monitoring data at rest. It's by monitoring data that is streaming through live, real time. So it's very important that we act in a timely manner and make sure we have all your data before we run off and start evaluating it. So let's zoom in just a little bit and take a look at the way the pipeline works. Now, this might look complex, but we're going to deconstruct it a piece at a time. And this is a very simplified version of the way that data flows through New Relic's alert system. So first we have your data over here on the left-hand side, these little purple dots. It's coming in from whatever source, and we're filtering it based on the where clause in your NERCL query. Now, this is key. This is pretty important, but we're going to come back to it later to talk a little more about that where clause. So whatever is left after your where clause filters out data is what is streaming in to an aggregation window. So this can be any number of settings, but let's go with a default of 60 seconds just to make it easier to think about for now. Now, there's going to be a delay because it's imperative that we have some confidence that all of your data timestamped for that window is in that window before we aggregate it. So once we aggregate it, we're going to use whatever aggregation function you specified in your NERCL query. This could be average, sum, min, max, whatever aggregation function you used, we're going to apply to however many data points have arrived in that aggregation window. Once we do that, once we aggregate that data down to a single aggregated data point, we can't add more data to it. That's why it's so important that we have confidence that we've received all your data for that window. So you see this dotted line. That's because before then, we're dealing with the raw data that's coming in, that's streaming in. But now we have an aggregated data point, and we can hand that off to the evaluation pipeline. So that aggregated data point comes in, and it triggers the evaluation process. Now, the only thing that triggers the evaluation process is incoming aggregated data points. So as we're talking about this, let's imagine you have a threshold duration of 5 minutes, and your threshold is something along the lines of for at least 5 minutes. So what the system does is it inserts this new aggregated data point into its memory of the last 5 minutes. So it has a good picture of what the data looks like for the last 5 minutes, and it compares this data versus the threshold that you set up, the numeric threshold. And it asks itself, are all 5 minutes of data breaching the threshold? If yes, well, then we need to open a violation. But if a violation is already open, well, then are all 5 data points in the window under the threshold or not breaching the threshold, I should say? Okay, well, then it's time to close the violation. And in a nutshell, that's how this system works. That's pretty simple, right, Brian?
Well, Sorry, I had to figure out how to get my screen back on here. It is pretty simple. I'm seeing Scott's animation there throwing me off. It is pretty simple. That's a little bit of sarcasm. It can get complicated, right? This is a going beyond the basic session. So we want to get deep and help you understand what's happening behind the scenes. But we don't want to make alerting at New Relic difficult for everybody. We want everybody to participate, right? So a few things we're doing, and then we'll get back to the details, right? One, if you are bringing out a new technology, I don't know, Kafka, Elasticsearch, something, and you may not know what it is you want to alert on, what signals you want to monitor. Well, that's why we've just recently announced New Relic IO, which has a catalog of different types of services that contain, integrations for how to monitor them, dashboards for what to monitor, and alerts for which signals you should monitor at what particular levels as a starting point. This allows anybody to quickly, in a few clicks, get up and running with monitoring and alerting at New Relic with minimal knowledge, right? Great. The other thing we're doing is we're switching from alert creation being a bit of a siloed process. I'm going to go create alerts to, while I'm using the product, while I'm doing an investigation, a post-mortem, I find a particular query or a signal that I should have been monitoring. Right? I may have had a gap in my coverage. I want to add an alert condition for that signal right then. So whether it be that you're looking there at in the query builder, run a query, click right there, create alert. Or if you're looking at a chart, you can go to the action menu, the little ellipses, and say create alert condition from there. And as soon as you do that, a slider comes out from the right-hand side showing you that form for building an NRQL condition, a NRQL condition, as we say. And the NRQL query will be filled in. Don't go so fast there, Sean. The NRQL condition will be filled in, and you can accept it as is with the defaults, or you can fill in some additional information, add it to a policy, etc. Right? And then continue on your process. Okay, that's when you're working with signals directly, right? You already have all the information that you need in order to build a condition. But what if you have a lot of entities in your platform of different types of service, and you just don't know what to do, right? The New Relic IO didn't fulfill your need. So when you look at a high density view, sort of an overall view, looking at your entire estate, like you can with the navigator view, you'll see all these little hexagons, right? These little beehive looking things. The ones that are gray are the ones that most likely do not have any alert conditions defined for them. So what we've done is when you click on one of those entities specifically, based on the entity type and the tags associated with that entity, we look across all alert conditions in our platform from all of our customers in a very anonymous way, and we see what are the ideal conditions, or what are the most common conditions, I should say, alert conditions that are created for this type of entity with those tags on it, and we recommend alert conditions for you. Here in this situation, we recommend about 6 or so conditions. You can accept them. They'll use our baseline method, which starts with anomaly detection. You can use that approach, requires very little knowledge, or you can go into each one, tweak it, tune it as much as you want, and you can apply some of your advanced knowledge you have here, right? So we're doing things to make alerting easy, in addition to giving you controls to go deeper. Speaking of going deeper, let's go back to Sean.
All right. You came here to learn about the advanced settings. So let's start talking about that. First, what do we mean when we say advanced settings? Well, on the left here, you see a typical NRQL alert condition and the edit screen. If you look down a little bit below the mid of that screenshot, you'll see where it says fine-tune advanced settings. And that's what we're talking about. This is a blow up here on the right. You'll see there's a loss of signal setting where you can choose 2 options for the behavior to take when a lost signal is detected. You see some data aggregation settings there. There's a streaming method radio button, so you can choose which streaming method you want, as well as a delay to select and configure. And finally, you'll notice there's a gap filling strategy down there. Well, what does this all mean? Let's break this down. First, you have an aggregation window duration. Now, this used to be fixed at 60 seconds, but as it is now, it's user configurable. So you can take that all the way down to 30 seconds, and raise it up to a maximum of 15 minutes. In the near future, we're going to raise that up to a maximum of 2 hours. What does this mean? This is basically the size of the window where we're collecting data. And once we aggregate the data, you're going to have a 60-second data point or a 15-minute data point, or in the future, even a 2-hour, a data point that represents aggregated 2 hours worth of aggregated data. You've got a loss of signal setting. And this is essentially us asking the question, how long should we wait after we stop seeing data coming in from your signal before we consider it a lost signal? Your options are you can open a new loss of signal violation, you can close all existing violations for that signal, or you can do both of those things at the same time. So this is useful if you have sporadic data coming in. Maybe the sporadic data wound up opening a violation, but now the data has just stopped reporting. So you can set up loss of signal to say, hey, close all open violations when that happens. The key thing to remember with loss of signal is that it needs at least one numeric data point before it considers it a signal that can be lost. So if you set up an alert condition with a loss of signal on a complete absence of data, our system won't know to think of that as a signal that's been lost because it hasn't ever seen the signal to begin with. So you always need at least one numeric data point, and that allows us to identify a signal, which then, if it disappears, if it starts reporting no data at all, we'll eventually consider it lost based on your configuration. Finally, we come to gap filling strategies. Now, we do not insert zeros into the evaluation stream when there's no data. So it's important for you to address those situations. And one way to address those is loss of signal detection. But what if you lose signal for just a couple of minutes and you have your loss of signal set up for much longer than that? Well, that's where gap filling comes in. It tells us what to do when we see a short gap where there is no data. Your choices are none, last value, or static value. So that means you can choose a static value. Many people choose 0. So when we do detect a gap, we retroactively insert zeros into there. But you can also choose last value, which will take the last value that was reported and continue it throughout that gap. Finally, you can choose none, which essentially turns off the gap filling settings. But keep in mind that it will reset the threshold duration counter. So what that means is if you have a 5-minute threshold and you have, let's say, 4 minutes of violating data, but then you have a gap and you haven't set up gap filling, then we will just restart at the beginning when we start seeing data again with minute 1. So it's important to set up gap filling for your alert condition. With gap filling, the important thing to remember here, much like loss of signal needs a single point of data, gap filling needs to see 2 points of data. It needs to see a numeric data point before the gap. It needs to see a gap, some period of time where there is no data coming in for that signal. And then it needs to see another numeric data point. Once that second numeric data point shows up, we will retroactively fill that gap with however you've configured it to be filled. And if necessary, open a violation if we notice that suddenly we have a bunch of breaching data points. So here's the really meaty part, and this is what's recently been released and is really exciting. It's the culmination of everything, the reasons that we've been really introducing this streaming alerts platform is to get these streaming aggregation methods out, which are really cool. Brian, would you like to talk some more about these streaming aggregation methods?
Yeah. Again, so what is a streaming aggregation method? It's a new term. We just relatively introduced it relatively recently. And what this is when we have a streaming system, what moves that streaming system along, right? If you have a river flowing, the water behind it moves the system along, right? There's a water flowing situation. Previous to when we released these new streaming aggregation methods, we'll talk about in a minute, the system moved not by the pressure of the data behind it, but rather by the movement of the clock, the new Relic clock. So if you had a 1-minute aggregation window, like Sean just described, for example, at the bottom of every minute, we would say, hey, look at the data that has arrived that matches this window of time, 12 to 12:01, right? And look at the data in that data, all the data points in there, and run my aggregation function on them, and emit that one data point, right? Now,
Sorry.
what we've done is we've moved away from this strictly clock-based model. You can leave the slide there, Sean, fine. Move away this clock-based model to a system where the event data moves the system forward, right? This allows us to improve the accuracy, right? Reduce alert latency, increase time to detect, or decrease time to detect, I should say, and also reduce false alerts, whether that be false positives or false negatives, right? So before we talk about the differences between these two new methods we released, let's look at different data flow patterns. Again, because this is a stream of data, you can go to the next slide, there you go, thank you. Because this is a stream of data, it's important to understand the shape and nature of how that data flows in, right? Most things that we monitor in this space are metric time series data. That means in these situations where some agent, our agent, third-party agent, collects data on a regular, frequent, and consistent interval and publishes that data to New Relic. So here in this top set of data points, right? Each of these dots being a data point. These are coming in consistently every 30 seconds. CPU measurement, CPU measurement, CPU measurement, right? Goes on forever, never stops. You may be monitoring one signal from one entity, or you may be monitoring that same signal across 1,000 entities, and averaging across there, for example. But still, each individual time series is frequent and consistent. Very common pattern. Sometimes you'll monitor for events. Give me a count of errors, right? In that case, hopefully you are not having frequent and consistent errors. That's a bigger problem. But hopefully you're having inconsistent and infrequent errors happening in your product. There'll be big gaps between when these data points flow in, right? So that's a different streaming pattern, and therefore the triggering logic, the motion we use to move the system along will be a little bit different. Now, the worst case of all is AWS CloudWatch data and a polling method, or GCP or Azure. I don't want to single out AWS, but where you have to go ask somebody else, hey, give me all the telemetry data points you have for the last 5 minutes, or actually since the last time I asked you, right? So you get batches of data that are probably inside that batch, frequent and consistent data points, but who knows when you'll get them. So again, streaming systems, time is relevant, right? Now, I'll make a quick plug. Say if you're using AWS CloudWatch data, please take a look at our AWS streaming metrics capability. AWS recently released this, and we support that. And that takes your batchy, chunky data flow and makes it more of a consistent, frequent data flow. So with these three models in mind, let's jump forward and talk about one. We'll talk about a little more detail about what we had before, still have, unless you change them or created a new method within the last month, and a new condition in the last month. You are using this aggregation method that we've given a name to called the Cadence Method. Again, the clock moves it forward. I mentioned it briefly. At the bottom of every minute, the clock moves it forward. If your data is coming a little bit slower, right, it takes 2 more minutes before your 12 to 12:01 data flows in, unless you add what we call and used to call an evaluation offset. Meaning you say wait longer, actual time, wait longer for that data to arrive. What's going to happen is that window is going to flow forward. It's going to leave without that data being there. And you're going to be like this poor guy here who was waiting for his train and says, I was only 30 seconds late. But the train don't care. He's not on it. He's the data point in this situation, if you haven't followed along with this metaphor. The train is your window, right? And you see the clock above him because the clock keeps going. It doesn't care, right? So in that method, the only way to increase your accuracy is to add latency. And that's an unfortunate trade-off. We want accuracy, we want reliability, and we want low latency. So we have introduced 2 new methods that are event-driven. Going forward, there you go. Now, if the tyrannical train was our metaphor for the Cadence method, our metaphor here is going to be, I don't know, some Waymo robotic limousines here, right? I'm going to make them robotic because drivers can be impatient. These little vehicles are very patient. It has a reservation for you, your data point. If you, the data point, are an hour late showing up, it's going to sit there and wait for you, right? It's the event of you arriving that activates that window of aggregation window, right? And once you arrive at that window, the question is, wait, how many are in your party, sir? If it's just one, that you know, by the time the person shows up in the car behind you, you're ready to go, right? No need to wait for anybody else. You showed up, another car shows up, pushes the machine forward, right? Again, back to that flowing water analogy. The data behind it moves the machine forward. We reduce latency, we increase accuracy, right? Now, if you have 1,000 mobile devices sending in telemetry from around the world, physics, there's going to be some delay between all those data points arrive. So you may start to receive data points for the subsequent window before the current window is fully populated. So you may say, well, I'm going to give it 2 minutes from the time I start to see new data arrive for the next window, before I believe that I have all the data for this window. Now, the thing with this event flow method is there's only one perception at a time. It doesn't have a clock. It doesn't have a timer. It only depends on the data point showing up, pointing to the timestamp in the data point and saying, this is the time. So when a data point goes up and says, here's my time, it maps it to a window. When another data point comes up and says, here's my time, it goes, oh, that time is 2 minutes after that data point. That window is, or actually, since the end of that window, it's closed, hasn't moved forward, right? It only knows about the time that the data points show. So if there are disruptions down the stream, whether that be for the internet, your environment, our system is showing up, that the data will sit at rest and wait for the data to show up, and then we'll proceed forward. So I got distracted by someone knocking at my door right there. Working from home. So that is the default method, which works for most cases. However, say you only get a data point once every hour. I don't know, you're reporting on the volume of data in your S3 bucket once an hour. I don't want to wait an hour for the next data point to come by and push that data point out, right? Or if you have this batchy situation where you may get data all of a sudden, moves forward, and then you don't get more data for another 30 minutes, and you wait. You don't want that data to get stuck in that pipeline because there's no back pressure pushing it forward, right? What you want is for the data to arrive. Says, well, I know I don't expect any more data to show up for another hour, so I'll set the lowest amount of time. I'll just say 5 seconds. Yeah. If after 5 seconds you don't receive any other data points for this, please proceed down the process, go down to be evaluated by alerts. Right? Now, in this case, event timer is a bit of a hybrid. So the event activity with the timestamp maps it to the waiting, robot car in this situation, the waiting time window. Then it says, well, how long should I wait by my little, kitchen timer, if you will, all right? To say, if this timer expires before another data point shows up in this window, then I'll assume I have everything I need, and I'll move forward. So that way you can look at unreliable or inconsistent data points and add reliability and consistency to that data flow. And that's the event timer method. Again, that all comes down to reducing false positives, increasing accuracy, and decreasing time to detect, while providing default settings that apply reliably to most scenarios, with an additional option, the event timer, to apply to those atypical situations.
Okay, just wait a second. What about loss of signal, though, Brian?
Yeah, well,
is loss of signal still waiting for data to show up? I mean, I want my loss of signal to let me know when my signal is lost, not sit around and wait for my data to show up. That's why I wanted to butt in here, because loss of signal exists separate and apart from these aggregation methods. And what you configure in loss of signal is how long we should wait, since we saw the last data point come from your signal through our ingest gateway. So essentially, it's a separate timer that's sitting off to the side here. So in this example, we've got signal is lost after 10 minutes. So that timer is for 10 minutes. And every time one of your data points comes through our gateway, the timer is reset to 10 minutes. If that timer ever counts down to 0, that means 10 minutes have passed since any data points have come through from this signal. That's the point where we jump in and execute one or both of these behaviors that you've configured. We can open a new loss of signal violation, letting you know, hey, your signal's lost. Or we can close all existing violations for the signal that was lost. Or we can do both of those. This is great for closing violations for sporadic data. Like, for example, maybe you're counting the number of synthetics failures. So if you ever have a numeric count value, then you know that bad things are happening. Your synthetics monitor is failing. However, if the data dries up, if we start getting no data at all, well, that means there are no more failures happening. And that's not numeric. That's an absence of data. So you need to configure this to say, hey, if I have an absence of data, close any open violations. And this absence of data is important to be aware of. This is all based on your where clause filter. So in your NERCL query, you create a filter using a where clause. And if our system does not see any data after running the where clause, it does not run your aggregator for that window. It simply sends us no data. So whether that be a sum, we're not going to try to aggregate no data and tell you it's 0. Minimum or maximum, we're not going to try to aggregate that and tell you it's 0. It's simply null. But it's important to know that that works for count and unique count as well. If there's no data there, you're not going to get a count of 0. You're going to get a count of no data. So it's important to remember that when you're setting up your alert condition and ask yourself, what does it mean when no data comes through for this signal? If you're counting synthetic failures, then that's a good thing, and you want to close open violations. Now, why would you want to use these two in conjunction with one another? Well, imagine you have a NERCL condition set up that is monitoring the CPU usage of one of your servers. And your threshold says, if that CPU goes above 90% for at least 5 minutes, I want you to open a violation. Okay, so imagine your server does. It goes over 90%. It's at 92%, and then it's at 95%, and the next thing you know, it's at 98% and still climbing. So obviously, we open a violation on that. But then that server crashes. That means the data stops flowing into New Relic. That also means we have no numeric CPU metric to compare against your threshold. So we leave the violation open, and there's no way we can close it now because no data cannot be compared to a threshold of 90. So if you have your loss of signal set up well, then after 10 minutes of losing signal on that server, you open a loss of signal violation to let you know, hey, this server has probably crashed. And at the same time, you close any open violations, such as a CPU violation or a memory violation, because those are no longer important, and there's no way we can close them anyway. So that's how you would use those in conjunction with one another. Remember, this is based on the length of time since we last saw a data point. So we don't care whether you're using event timer or event flow or cadence. This exists separate from that and is constantly vigilant. Do be aware, though, that when there are lags in the data flow, this is sensitive to false alerting. Now, remember, these lags can come from your instrumentation. They can come from any sort of transient network issue in the internet between you and New Relic, or it can even be a problem with New Relic. When stuff happens to stop the flow of data, loss of signal does not stop watching. It's entirely vigilant. And so you can get false alerts when that happens. So be cautious when setting loss of signal, and don't set it too low or you'll wind up getting a lot of false alerts. Also, you probably don't want to use this if you're using a polling-based source, because that's a situation where New Relic is reaching out to a third party for data. And we have no idea if that data is going to come immediately or in 30 minutes. We can't be responsible for that. So if you set a loss signal of 10 minutes, you might wind up getting false positives on that. Brian, why don't you talk about the use cases for event flow?
Yeah, exactly. Well, let me talk about just go back to the common use case, right? Where we're talking about metric time series that come from agents such as our agent, open telemetry agents, any open source agents, etc. Where again the data comes in a consistent and frequent manner, right? Let's look at the set of these different configuration settings we discussed, how they apply to this use case, this scenario, and sort of talk about the different settings that we should use for this common scenario. Then we'll talk about a few, the other two alternate scenarios, right? So again, agents, third-party open source tools. Now, typically, because your signal is coming along, expect it to not have gaps. A gap situation may occur. A great data point happens, something happened to that middle data point. Who knows what? It's an asynchronous universe. Another data point comes another minute or two. There's a gap. I didn't expect a gap, so I will typically recommend to choose last seen value as your gap filling strategy. So that line kind of keeps continuing as if data points were there and fills in. It's sort of a straight line kind of approach in a sense. Now, the aggregation window, how long do I collect data points before I run that one aggregate function, right? This is typically, if I want to look at a normal flow of data and react to it, then I would say align your aggregation window to the frequency by which your agent publishes data. So if your agent publishes data every 30 seconds, make your aggregation window 30 seconds, right? If you have a very jittery source or an erratic signal, you might want to space that out a little bit so you can average some of that erratic values into a more consistent value. But typically I say start with aligning it to the published frequency of your data. Aggregation method, stick with the default, right? Event flow is typically your friend, unless for some reason you have lots of space between your data points arriving. Right? Now, if you have a single entity producing a single signal, right, and you've aligned your aggregation window to the frequency by which you publish data, I would say crank the delay down to 0. You don't need to wait. A data point comes in, another data point puts it forward. There's no need to wait, right? Keep it flowing. However, again, going back to that situation, if you have a distributed data set, or there's a little bit of clock skew, someone asked earlier about clock differences, right, and that data coming in, then you're going to want to keep some delay that maps to how your data flows in. Again, looking at the timestamps in your data, this isn't clock time according to the wall clock. This is the timestamps that show up and the sequence by which they show up. So if you have some natural jitter in your arrival of the data, either keep the 2-minute delay or experiment with turning that down if that extra minute is precious to you. But probably if you have 1,000 nodes reporting in, that 1 minute or 2 minutes isn't that critical for you necessarily, right? So in general, I say keep the defaults. Lots of signal. Again, be selective about where you apply lots of signal. If you have one entity that produces 10 different signals, do you need to be alerted if any of those signals are lost? Or do you pick one like CPU, which will always be there, for example, for a host, to be the proxy that you're watching to identify when that entity disappears, right? And then set a timer duration that aligns to your SLA. Again, like Sean mentioned, if you're too tight, you want to say 30 seconds if it's offline, you're probably going to get false alerts because there's latency or there's some lag built into an asynchronous distributed messaging system, right? So don't be too tight with that loss of signal setting. And oftentimes you will want to pick both closed open violations and open and new violations so you can clean up the noise and be notified of a problem. So that's some sample settings of your most common scenarios, right? But let's jump into less common environments.
Less common environment. You see, you might notice, you might recognize this diagram from earlier in our talk. Where there's a couple of different kinds of common signals. One of them is inconsistent data. Brian used an example of counting the number of logs that have the word error in them. Now, ideally, you're not going to have these very consistently. These will show up. Maybe you'll get 5 or 6 in a minute, but then you might have 24 hours where none show up. If you're looking at a set of data like that, where either the data is completely inconsistent or it's just very sparse, maybe you have 4 hours between data points, or maybe even 24 hours between data points. You already know the data is going to be that sparse. You don't want to rely on event flow for that, because event flow relies on back pressure from data coming in to push the current data out. Instead, these work really great with event timer. Another use case for this is synthetic monitor failures, which I talked about earlier. Maybe you're counting the number of failures you have from your synthetic monitor, and you could go days without having failures, but suddenly you start having a real count of failures. And what you need is for that to be aggregated quickly and reliably. So event timer is a better method for these particular use cases. Now, remember, if you're relying on a 0 value to open or close a violation, you will want to use loss of signal. Gap filling is of less use here because gap filling needs to see that second data point to identify that there is a gap. And since you have no idea when that second data point is going to come in, or you know it's going to be a very long time, you don't want to wait all of that time for your violation to close. So you can use loss of signal to say, hey, if I'm not seeing a count of errors, or if I'm not seeing a count of synthetics monitor failures, well, then go ahead and close my violation. Now let's look at this bottom one here, which is batch aligned events. Typically, what I think about when I see these is our cloud integrations with AWS, GCP, and Azure, because on almost every service, we reach out every 5 minutes via an API call and request 5 one-minute data points. So in that case, we know we're going to get batches full of 5 one-minute data points. You just don't know when they're going to come. And so again, since this is a batch aligned data stream, event timer works best for this, because you don't know when it's going to come, but you know once it does come, you're only going to get 1 data point for each aggregation window of 60 seconds. So why wait around? Instead, just set a 5-second timer, which is the lowest setting for event timer, and aggregate that data within 5 seconds of it coming in. For this particular use case, I would not recommend using loss of signal, as I said, or if you do, because sometimes you want to know if your AWS service goes down, just make sure to be cautious if setting it for a low value. I would recommend setting it for a higher value so that you don't wind up getting a bunch of false alerts just because there's some response slowdown from your cloud service. If you'd like to know more about this and maybe ask questions or participate in the discussion, I wrote an article on discuss.newrelic.com, which is our Explorers Hub, our forums. The article is called Relic Solution: How Can I Figure Out Which Aggregation Method to Use? And, you know, everybody asks this question, and I have asked this question. If New Relic has a better idea than I do which method I should use, then why don't you just pick the right one for me? And believe me, now that we have this feature out there, this is one of the biggest improvements that we want to make. Since we are the ones ingesting your data and we have the best idea of the shape of your data as far as when it comes in, then we should be the ones to say, hey, based on this, we really recommend event timer or event flow. So we don't have that yet, but I'm working to make sure that we can deliver that to you and make things a lot easier. And of course, you can always fiddle with the dials and knobs, and play with those advanced settings if you still want to.
Excellent.
Well,
we've answered a few conversations, questions in the chat. We're hitting up against our time barrier.
All right.
I would say read those. I think one of the takeaways from John's statement is that we started out with defaults that we believe cover most of the settings. We've given you the controls to accommodate for those abnormal scenarios. We've chosen delay settings which are a little more generous with time in order to sort of err on the side of accuracy. But if you want to prioritize time over accuracy, you can crank that thing really down, right? Someone's asking a question about if I have errors, I only want to know if I get one error, tell me fast. You can crank that delay down to say as soon as you get that one error, wait maybe 5 seconds for another error spin, then tell you. Now, you may have a violation chart that shows fewer errors than you get. You may have to click through to go look at the data in the storage system to look at the actual error counts, because you've prioritized that signal to focus on speed of throughput versus accuracy of the data. By typical, I'd say make a 1 minute window and a 1 minute timer, so you know that you're getting 100% of the data that should be aligned to that window, right? But again, that's your choice. If you want to sacrifice everything else for the holy grail of time to detect, you can do that. So again, read that article, and let's continue this discussion in the Explorers Hub. Take care.
Absolutely. Take care, folks.